recommend definitely reviewing somehow though, because we did cover quite a few things. Okay. All right, hopefully that picks up on the iPad all right. So picking up where we left off, one thing that we focused on a lot on Tuesday, basically the main thing, we looked at the action potential graphs for the contractile cell versus the autorhythmic cell. Today in lab, we are going to go over the anatomy of the heart a bit more, and we're going to get to dissect hearts. You should be excited because dissecting hearts is super fun. These are not preserved hearts, these are real hearts, they have blood in them, and they're really, really huge. So it's really my favorite dissection, and if you have done the lab manual pages before lab, so please do those. It makes it go a little bit quicker because I hate rushing through and say, here's you 10 minutes to look at the heart because they're really fascinating to look at. Yeah?
What animal are they coming from?
They're coming from a large hog. They are donated to us from a slaughterhouse. So that's how I get them. I get all my organs for AP2 from a slaughterhouse. I just go whenever they're slaughtering one day and ask for whatever organs I want. So they'll give me they give me bags of kidneys, bags of hearts, bags of lungs, tracheas, the uterus, all kinds of stuff. So they'll just cut them out and give me big bags, and I just put them in little bags, freeze them, and then rethaw them, and then we dissect.
Is that your candy shop?
Yeah. Kind of gross, right? Not really fun to get huge bags of warm organs, but it's cheaper and they're much better than the preserved organs. Anyway. All right, so a little bit about the heart. Since we went through the electrical signaling last Tuesday, some of the comparison of the ATP production in cardiac muscle cells. So your heart relies almost exclusively on aerobic cellular respiration. So you know the heart muscle is going to have a lot of what?
Oxygen.
Oxygen, right. Oxygen and mitochondria are essential to the heart. This is why the heart has so many more mitochondria than the skeletal muscle cells. So we're kind of, forgetting things like the fast glycolytic fibers versus the slow oxidative. All of this uses aerobic cellular respiration because your heart needs to pump constantly. This is why cutting off the oxygen supply to the heart can be very, very lethal. If you have blockages in those little coronary arteries that supply oxygen to the heart muscle themselves, then they can cause myocardial ischemia, basically with blockages in the heart, which can eventually lead to myocardial infarction, which is a heart attack. So their oxygen source, mostly coronary circulation. We'll talk a little bit today in lab about the individual vessels of coronary circulation, and these are vessels that are called anastomoses. And what that means is more than one vessel supplies the same area. And you have these in several areas of your body. But if one of those gets blocked, then, well, not exactly, because there's more blood coming to that area. Now, it's not good to have a blockage, but you'll notice that some of the arteries encircle the heart kind of like a crown. So there's more than one area for blood flow to get there. They also have lots of myoglobin in them, and we talked a little bit about that last week. Myoglobin, there's very red fibers in the heart, and they carry oxygen on them. So the fuel for aerobic respiration is a little different than the rest of the body. We said the body tends to like to use what molecule for energy? Well, they use ATP, but what do they use to make the ATP? What? Okay, they have oxygen. What starts out in the whole cycle in glycolysis? Glycogen breaks down into, what's in between glycogen and pyruvic acid? Glucose, right. So they like to use glucose. Your heart relies mostly on fatty acids. It uses 60% fatty acids, 35% glucose. Something else that's interesting is your heart can use a lot of things. It also will use lactic acid, amino acids, and ketones, and these are particularly true whenever they can't get to other things. During exercise, their utilization of lactic acid goes up because you may produce a lot more lactic acid during exercise whenever the fibers in your skeletal muscles run out of oxygen. So they'll produce lactic acid by glycolysis, and your heart can utilize that. They may start to use amino acids from breakdown when you run out of other sources, and they can also even use ketones. Do we remember what a ketone is? Forgot to bring my M&M's for you.
It's like a chain link.
Sorry?
Never mind.
That's a type of what? Not exactly. Nobody remembers what a ketone body is? Ketones, yes ma'am.
Is it an amino acid that it kind of doesn't like use glucose? It uses fat.
Okay, well you're on the right track here. So ketones are produced by beta oxidation of fatty acids. So we said that those body cells like to utilize glucose. When they don't have glucose, they can utilize fatty acids, but they tend to produce ketone bodies as a byproduct. Now ketones can lead to ketoacidosis. They can make the blood more acidic, and this is what can lead to diabetic coma. So usually that's the only time when it's an issue. During starvation, when your body is utilizing fats on large scale, they don't have glucose to use, and during diabetes, whenever the cells are unable to use glucose, so they're large scale oxidizing fatty acids, and that's what can lead to ketosis and diabetic coma. But these ketones can be utilized by the heart from beta oxidation of fatty acids by the cell. So all of those are going to be important in situations where they cannot get these two things, and particularly in exercise. And they rely almost exclusively on aerobic respiration, but some of the ATP does come from creatine phosphate. So do we remember what creatine phosphate was from skeletal muscle?
A fast way for energy.
It's a fast way for energy. Remember, it powered skeletal muscle for about 15 seconds. Whenever you were at rest, your body loads phosphate groups with an enzyme, this creatine kinase, onto the creatine phosphate, and then you have energy that can power quick bursts for 15 seconds. So it does use some of that. Therefore, creatine kinase, that enzyme in the blood, could indicate a heart attack. Now, something else for you to be aware of, one of the major things they look for in the blood to see a myocardial infarction or a heart attack when the heart muscle tissue has been damaged is troponin. So they measure troponin in the blood. They can also look for things like myoglobin. So those things, troponin, creatine kinase, myoglobin, are not usually things found in the blood, so those could all be indicators that someone has had a heart attack. So it's showing heart muscle tissue damage. You might have asked about that last semester. Yeah, yeah. Yes, yeah. And to be honest, I'm not positive why they look exactly for troponin, but I know that's one of the major indicators that somebody's had a heart attack is the troponin.
So what causes it to go in the blood?
What causes what?
What causes troponin to go in the blood?
Well, whenever you have a heart attack, you basically have cardiac muscle tissue damage. So you're blocking off oxygen to the heart, so you have those tissues die and break down, and then you have some of those components from the it's toward the sarcomere coming out into the bloodstream. So it's just an indicator of damage. So same thing, if you had skeletal muscle damage, you would notice things like myoglobin in the bloodstream as well. All right, so electrocardiogram. I'm not going to spend tons of time on this in lecture because next week's lab, we talk a lot about the cardiac cycle and the EKGs. We do have some EKG machines in the lab. Now, if anyone uses them in a hospital, you'll be somewhat disappointed because the EKG machines we have, I think it's kind of funny myself, but the brand that's on the box says discount cardiology. So I think it's funny that there's something that's called discount cardiology, but it'll give you an in general overview of how the electrocardiogram will work. You can hook it up to yourself and see just a very rough EKG reading. So we're going to talk a little bit about this just to kind of relate the electrical signals. Now, since we have this little graph on the board here, I am not going to attempt to draw this out because you guys have seen my drawings. This is interesting. I did have 2 erasers, and today there's only 1 eraser. So somebody has stolen one, and I liked 2 erasers. Okay, anyway, the electrocardiogram is going to record action potentials of all the active cells in the heart, and you can attach leads to the skin. You don't even have to go into the body. And because of those changes in ions in the extracellular fluid, you can pick up these little electrical changes on the skin surface. So it's measuring it in little millivolts. Now this is showing an average cardiac cycle. We can do this in lab and you can find your average cardiac cycle, but an average cardiac cycle in somebody that has a normal heart rate, which is an average heart rate, we'll say, at 75 beats per minute, is going to have a cardiac cycle that is 0.8 seconds. So if you divide 60, so 60 seconds in a minute by 0.8, you'll get 75 beats per minute. So this is where that comes from. Now just so we understand what one cardiac cycle is, I have this on a slide later on. Maybe I should move that slide up. But I'm going to go ahead and write it. So one cardiac cycle consists of atrial and ventricular, systole, and atrial and ventricular diastole. So instead of using the words contraction and relaxation, we're going to start to use the terms systole and diastole. So systole is contraction and diastole is relaxation. And I like this particular little graph here because it's showing in blue, this is atrial contraction, and yellow ventricular contraction. So it shows the systole or the contraction of both atria and then both ventricles, and the diastole, the relaxation of atria and ventricles. Now, I think I just said that wrong. This doesn't exactly show that. This shows the depolarization and repolarization. This only shows the electrical signaling in the heart. But remember, things have to depolarize to contract and repolarize to relax, so you can relate that on here. So one cardiac cycle consists of atrial and ventricular, systole and diastole. So we start out here at 0, and the first little hump you're going to see right here, so it happens about 0.1 second and ends at about 0.2 seconds in an average person, is going to be called your P wave. So that little bitty hump there that you'll see is a P wave. The P wave represents the electrical events that lead to atrial depolarization. So which chambers are your atria? The top ones or the bottom ones? Top ones. Are they more thin-walled or more thick? Thin-walled. And I know that you guys are little, we'll talk a little bit more about this in lab today, just because we're somewhat behind. We didn't talk as much about that since we had our snow day. But atrial depolarization is going to be a little bit of a smaller event than the ventricles because atria are smaller. Their muscle is not as thick because they only have to push blood down into the ventricles. Now sometimes atria can be overworked and they'll have to thicken because of a ventricle that is hypertrophic. It's not really working well. So after that 0.2 seconds, we have this really strange looking thing on the EKG. This is always going to be obvious. It goes down to this point called Q, up to the R, so this is where we have the highest point on the EKG reading, and down to the S. And we call this the QRS complex. The QRS complex represents ventricular depolarization. So this is the electrical events that cause the ventricles to depolarize. And notice that stops here at around 0.3, 0.4 seconds. Now at about 0.4 seconds, we see a little bit of a bigger hump come up, and that ends at 0.6 and then takes our whole cardiac cycle ending to 0.8. And this T wave, we call it, represents when the ventricles repolarize, so when they go back to their resting membrane potential. So we've got a hump for atrial depolarization, ventricular depolarization, and ventricular repolarization. What event are we missing here? Atrial repolarization, when the atrial fibers repolarize, so potassium leaves, and they relax. And they do that as your ventricles are depolarizing, because remember last week we said the atria contract, then the ventricles. Again, just so you've got it in your head, depolarization has to happen before cells contract. Repolarization has to happen before they relax. So why do you think we don't have atrial repolarization on here? Why do you think that doesn't show up on our EKG reading? Yes?
Does it
happen at the same time as the QRS movement?
Right. It's happening at the same time the ventricular fibers are depolarizing. So since the ventricles are so thick, so large, so they have so much muscle in them so they can pump out blood to circulation, this is going to be a much larger electrical event than atrial repolarization. So it's not that it's not on there per se, it's just overshadowed by ventricular depolarization. So that's why you don't see atrial repolarization on the EKG. That make sense? And the other interesting thing about this is by looking at time intervals, you can see lots of things that will happen here. So for instance, the interval from P to Q, this is the time that it takes for the atria all the way to ventricular excitation. You could look at the ST segment. This represents the full amount of time the ventricular fibers are completely depolarized, because this is right before they repolarize. This is the QT interval, which represents the amount of time from the beginning of ventricular depolarization to the end of ventricular repolarization. So you can estimate time intervals based on this. Now there is a way to estimate that because it has to do with the speed of the paper and how much each block is worth, but I'm not going to do that in here because we focus on doing that in lab because it's a little bit tedious, it has some of the math, and that's a lab thing, so that's what we have the lab EKG for. So in here I want you to understand it because I think it is essential to understanding some of the electrical events, but we're not going to go through and learn how to read all kinds of things on the EKG. And I'll go ahead and also mention that one thing we do not do in here is we do not learn how to read every abnormality on a 12-lead EKG. We have a course at Rome State that does that if you're interested in doing it, so you can get, I guess, a certification to do that at a hospital, but it can be a little bit more in detail. So we look at the regular EKG readings, but we do not learn how to use 12-lead EKG. So I realize that I've had plenty of students that are certified to do this. Again, you just have to take a course and you know how to do that, so I'm sorry if that's disappointing, but we don't do that anymore. Okay, so that was showing a normal cardiac cycle. I love this slide because this is showing how this actually comes about. Green represents depolarization, red represents repolarization. So notice when our P wave begins, this is when the action potential is fired at the SA node. How many times did we say the SA node fires a minute? 100, I heard 100. Okay, 100 times a minute. So it starts here, and then as it finishes depolarizing, notice now our atria can contract. They're pushing blood down into the ventricles. So now they're turning red, they're starting to repolarize. As our ventricles are turning green, they're starting to depolarize. That's when we get our QRS complex, and after all our ventricular fibers are depolarized, they can then contract. Then we begin our T wave in red because this represents repolarization. So here they're repolarizing, and as they're repolarized, our heart muscle relaxes, and this would be a cycle. So notice it would be 0.8 seconds, and this would happen every 0.8 seconds. So that would be in a normal heart rate of about 75 beats per minute. So again, one cardiac cycle represented here, atrial and ventricular systole, atrial and ventricular diastole. Yes?
So both atria and both ventricles contract at the same time, meaning that they're simultaneously pushing blood into each compartment, into the lungs, out of the heart all at the same time?
Yes, and let me, just to make sure everybody understands and doesn't get the wrong impression from there what you said, both atria contracted once first, then both ventricles contracted once. So yes, the question was they're pumping blood out into systemic circulation, which we talked about Tuesday, goes to all the body systems, and to pulmonary circulation to the lungs at the same time. Yes, so it's not like blood travels around the body, all of it, then goes to the lungs. So you've got some in the lungs and some going toward the body at the same time. Good question. All right, so this is what I just wrote on the board. All the events associated with one heartbeat. So at 75 beats a minute, one cardiac cycle requires 0.8 seconds. Now I'm going to write this on the board so we don't forget it. This is really, this should be a little intuitive, but they divide your cardiac cycle up into 3 major periods. They divide it into atrial systole, ventricular systole, and the relaxation period. So what we're doing is just looking at what we just saw in the EKG and what I have listed over there, the atrial, ventricular, systole, and diastole, into 3 major stages. And we'll talk about the events associated there. Really, the hardest thing about this is they add some terminology that you may not have heard of before. Okay. All right. So we'll first look at atrial systole. So what's happening here in atrial systole? First of all, it's good to remember that when the atria are contracting, so when the atria are in systole, the ventricles are relaxing. They're in diastole. Okay? So when the atria are in diastole, which means the atria relaxing, what are your ventricles doing? Contracting. They're in systole. So when the atria contract first, they are pushing blood down into a relaxed ventricle so they can fill them. When the ventricles are contracting, your atria are relaxing because they're receiving blood as well from your pulmonary veins and your superior and inferior vena cava. So they alternate, the atria and ventricles in systole and diastole. So that's important to notice. So what you're going to notice here first, let me just flip through this quickly, is you're going to notice this all adds up to 0.8 seconds. So atrial systole is their shortest time at 0.1 seconds. Ventricular systole is about 0.3 seconds. And our relaxation period is 0.4 seconds. So all of that, 0.4 plus 0.3 plus 0.1 adds up to 0.8. So this is what's happening in that 0.8 seconds. So 0.1 seconds, we're getting atrial systole. So we'll begin whenever the atria contract. Notice this has to happen after our P wave is formed, whenever all the fibers are depolarized. So the atria contract and the ventricles relaxed, and then you get something known as your end diastolic volume. So let me write it over here. Let's define end diastolic volume.
It's not word after ventricle. Following.
Following, yes. So the amount of blood in the ventricle following atrial systole. In other words, after the atria pushes all its blood into the ventricle, this should be the fullest the ventricle is. It is completely full. And then a number associated with it. An average end diastolic volume equals 130 milliliters. And this is per ventricle. I'm sorry there's a glare. I honestly have no idea what to do about it. Unless I just turn all the lights out. I really don't know what else to do. If anybody has suggestions, I'm open to them, but I really don't know how to fix that. So the end diastolic volume is the amount of blood in a ventricle following atrial systole. So that's a completely full ventricle. And it's normally about 130 milliliters. So after this phase, there'd be about 130 milliliters here and 130 milliliters here. Okay there? All right. A ventricular systole. Again, what does systole mean? Contraction. Just trying to get us used to using those terms. This is about 0.3 seconds. Your ventricles contract and your atria are in diastole, so they are now relaxing. So notice your right and left atria here relaxing. Your ventricles are contracting. They are pumping blood out, and we'll review this again in lab today, but your right ventricle is pumping blood into the pulmonary trunk. Your left ventricle is pumping blood into the aorta. So the events that happen, it's kind of going to be a progression here. So what you have in ventricular systole, and this is why I like two erasers. Let me remove this relaxation period a little bit. You first have something called isovolumetric contraction. That's our first part of ventricular systole. This is before it actually ejects blood into the pulmonary trunk and aorta. So when we think about the word isovolumetric, think about the word isometric and isovolumic. Anybody remember what the prefix iso is? Like when we talked about isotonic and the same, okay? Same volume here. And isometric contraction we talked a little bit about in skeletal muscle. Anybody remember what isometric contraction was? Okay, isometric, remember I talked about like I can, okay. So like I could flex my arm whenever and move it whenever I'm contracting it, right? Or I could push against a wall and I'm not actually moving the load. Right, doesn't change the length, exactly. So isometric, we can build up tension in the muscle, but we don't change the length. So one of the things we have to get used to when thinking about blood moving from chamber to chamber and from chamber to vessel is blood is going to move, kind of think about diffusion. That's not what's really happening here, but everybody tends to remember with diffusion is high to low, right? Blood is going to move from a high pressure to a lower pressure. So what happens when the atria fill the ventricles, and we're now in diastolic volume, so they each have about 130 milliliters in it, they build up tension here, and the pressure in the ventricles has to rise to a greater pressure than what's in the pulmonary trunk and aorta. When they do that, whenever the tension builds in the ventricles, then the valves covering your pulmonary trunk and aorta open, and you have ventricular ejection. So think about isovolumetric when the ventricles are closed chambers. So really brief period. These valves, the atrioventricular valves are closed and the semilunar valves are closed, but our ventricles are building pressure here without actually ejecting. So very brief period, it's a closed chamber, but the ventricles are full. That isometric contraction causes tension in the heart muscle, where the pressure in the ventricle rises above the pressure in these next two vessels. And when that pressure rises above, you get ventricular ejection. So it opens their pulmonary semilunar valve and their aortic semilunar valve. And then you have ejection into the pulmonary trunk and aorta. Okay. So after isovolumetric contraction, and we built tension here and made the pressure rise, then we have ventricular ejection. So now after we've had ventricular ejection, we would think our ventricles are now what? Are they full or empty? We think they were empty, but notice the volume remaining is about 60 milliliters. So that, two erasers are very important to me. That is going to be our in systolic volume. So let's just change this word. And you could probably guess this definition. In diastolic volume was the volume of blood in the ventricle after diastole. In systolic volume is volume in ventricle following ventricular systole. say here, ejection. So after the ventricles have contracted and ejected blood, this is the volume that remains in them. And it's normally around 60 milliliters. Can everybody see that? I need to read it out loud again.
Is this ESV the abbreviation?
Oh, I'm so sorry. Yes. Sorry. ESV. I did not change that. Thank you. And systolic volume is an ESV. So the volume in the ventricles following ventricular systole, following ejection, is 60 milliliters. Now, since we know the end diastolic volume, the volume when it was full, and the end systolic volume, the volume when it was, I'm saying in quotations, empty, we should be able to figure out how much blood is pumped per ventricle for each cardiac cycle, right? And that has a word too. Can I erase this? That is known as stroke volume. So, stroke volume is the amount of blood ejected per ventricle for each cardiac cycle. We'll abbreviate stroke volume SV. And it has a calculation. Your stroke volume is equal to your end diastolic volume minus your end systolic volume. So go ahead and just on your piece of paper somewhere, prove to yourself that you can do this. Use that calculation to calculate a normal stroke volume. Use the normal end diastolic volume and the normal end systolic volume. So what did we say our average end diastolic volume was? 130 milliliters. Our average end systolic volume? 60 milliliters. So an average stroke volume is 70 milliliters. Easy enough, right? So that's usually our volume ejected. What questions do we have so far? All right. And finally, our last phase of a cardiac cycle, this is the longest at 0.4 seconds. This is our relaxation period. And I like this little figure because it shows, as again, it's a time-lapse progression, what happens in each one. So 3 major things that are happening here. Isovolumetric relaxation, and then this is going on into ventricular filling. So, both the atria and the ventricles are relaxed. This is after our ventricular fibers have repolarized, and it's the time period when we're starting to depolarize our atria. We then have isovolumetric relaxation. What did we say isovolumetric meant again?
Stable blood pressure.
Okay. Isovolumic, keeping the same volume, isometric can build up pressure, but again, they are a closed chamber. So, the semilunar valves close, and you've got this remaining 60 milliliters of blood in the ventricles, and this is right before we have the atria contracting to push blood down into the ventricles. So that's isovolumetric relaxation. So, remembering the difference, isovolumetric contraction is when the ventricles are completely full. Isovolumetric relaxation, I don't want to say they're ever completely empty, but this is after we have ventricular ejection. They are more empty. And then you have ventricular filling, okay? So this is when you have atrial systole. Now let me just go ahead and explain ventricular filling, because if you notice here, it shows ventricular filling is part of the relaxation period, and then atrial contraction. For some reason, they don't use this word in Wiley. Let me go ahead and write relaxation period. But you got your isovolumetric relaxation. And then when you have ventricular filling, there's a little bit of ventricular filling that happens right before atrial systole, and it is called atrial diastasis. That's D-I-A-S-T-A-S-I-S, atrial diastasis. And basically what that is, when the atrial pressure has exceeded the ventricular pressure, it causes these atrioventricular valves in between the two to open. And before the atria actually contract to push blood into the ventricles, some of it just trickles down a little with gravity. And that's the diastasis. And then finally, so the atria can push all the blood that's remaining in them into the ventricles before these atrioventricular valves close, then you have atrial systole, atrial contraction. So some of it's just going to flow with gravity before the atria actually contract. So that's why you have ventricular filling before you have atrial contraction. Does that make sense? So again, these three phases of the cardiac cycle are somewhat intuitive, I think. It's just getting familiar with all the events that happen in each one. So just make sure you review those. Yes?
What was the dichrotic wave?
Oh, I did not mention that just yet, and I was going to say I didn't do that just yet on purpose. I will show you that on a minute on a pressure graph, so we're going to get to that in just a second. Yeah, sorry, I didn't mention that. Now this is just showing how all three of those phases and their timing relate to your ECG tracing. All right, so we're going to do a little exercise with this just to practice. But this is showing a pressure graph on the left side of the heart. So this green line is going to represent the left atrium. This blue line is going to represent the left ventricle. And this red line is going to represent the aorta. And it is showing the pressures. The thing to keep in mind, again, is blood is going to flow from an area of higher pressure to lower pressure. So when one area's pressure exceeds another, that's what causes blood to flow into the next chamber or vessel. So notice here, whenever the atria contracts and the atrial pressure rises above the, or I'm sorry, this is the atrial pressure. Here your bicuspid valve closes, and I know that we still have lab to go and review this a little, but the bicuspid valve is going to be the valve in between the left atria and the left ventricle. So after you have ejection from the atria, atrial systole, then you're going to have isovolumetric contraction. So notice the pressure goes up in your left ventricle. When the pressure in the left ventricle exceeds the pressure in the aorta, then the aortic valve opens and you have ejection into the aorta. Now when the left ventricle is pumping blood into the aorta, its pressure goes up. When its pressure starts to drop, then the aortic valve closes. Now here's that little dichrotic wave or dichrotic notch, explaining this a little bit. Remember, blood likes to go from a high to low pressure. When the aortic valve closes, and that's the valve between the aorta, the big vessel coming out of the left ventricle, and the left ventricle, pressure in the left ventricle is going to drop below the pressure in the aorta. So guess which way blood is going to want to go? Back toward the left ventricle. But the valve is closed. It can't go that way. So as it bounces back, your aorta has a lot of stretchy material in it. We'll talk about that with the blood vessels. But it's got a lot of elastic tissue. So it kind of stretches and then goes back a little bit. So it rebounds off of the aortic valve and then continues to flow throughout the aorta. And that's what makes this little notch on a pressure graph every time. And notice as blood flows from the aorta out toward your systemic arteries, it slowly starts to taper off in pressure. Okay? And then of course we go down to the atria again and have atrial ejection, so this begins to start over. So what I'm gonna have you guys do is kind of practice this yourself. It can be a little challenging, but that is the point. So if you have that worksheet that I handed out to you on Tuesday, go ahead and pull that out. And you're gonna turn to the very last page that has this pressure graph on it, okay? So go ahead and get into the base groups that I assigned you in.
You have another one.
I do not have another copy actually with me. Look off somebody else's at your table. And then after class, remind me and I will go see if I can find you a copy. Okay, so if you don't have a copy, look off somebody else's. I handed these out on Tuesday. You may or may not be able to do the matching yet, but what I'm worried about is the top part, the A through F. So see if you can fill those out, thinking about the pressures, and I'll come around and help.
Oh, right. And unorganized. I'm sorry, I'm thinking right. Alright.
Again, feel free to discuss things with your groups, that's what we have.
That's I think so. The next question is, what's this like holding out?
Sure. All right.
We just want to know for right. Then, what if in a group with pressure, the left ventricle has the left ventricle? So we're talking about this right here.
So in the pressure of the left ventricle, so your left ventricle is this line, rise above pressure of the left ventricle. So that's gonna be kind of right at this point, right? Because this is your, I realize that's how this up here, they're black and white, so I apologize, but still, left atrium keeps going here, left ventricle here. So here they're about the same pressure and right here it rises above. So what event happens right there? Right. Yep. That's fine. So I'll show you.
It's right there on the chart.
So, if this little line is your left atrium, so see if it continues to here. This line is the left ventricle. Notice right here they're the same. Here's where the left ventricle rises above the atrium. What event happens right there? Right. Some of these are easier than others.
No.
No.
If you get utterly confused, please let me know. It is a little challenging. How's it going, guys?
And the volume of the ventricle is decreasing.
So, let's look at this one. Left atrium.
During most ventricular pressure.
So it's
Yeah.
Yeah, then they.
Or you do this.
We don't, so we left that true. It's good introduction.
That's when they're full and closed.
So remember, you're in these groups to help each other. So if you need help, you're not working together. It helps to discuss.
And then they go and they go back. During one part of the group, it's like something blood pressure highs.
E is the hardest one.
It's the hard.
E is the hardest.
These are all
Tricky.
hard.
I think F is the hardest. During one part of the cardiac cycle, blood pressure highs in the largest systemic arteries. That would be
How's it going, guys?
ventricular diastole because the atria is an artery.
So,
Okay.
That's what all those
So let's think about these. During ventricular systole, so systole means
But
what?
it has to be ventricular diastole.
The blood volume in the atria is what? And the volume in the ventricle is what?
No.
So when the
It has to be
ventricle
ventricular
is
systole because of the
what
breath.
phase in the
Way
atria?
up here, yeah, pressure goes way up. It has to be ventricular systole.
Okay, so it's relaxed, so it's pressure decreasing, but
Yeah,
what's
when
actually happening in the atria?
necrotic notch, it's a little-
It's increasing, right? Because why? It's getting filled. Yes. It's a lot of thinking, it's hard. It is hard.
and then the volume of it is what is decreased, it's already full, so it's.
A and B valve closes. Okay, we don't know.
No, I'm not missing any more. Just probably really get used
So
to it.
first of all, let's see make sure we understand where that is. So there's your blood. So just in general, without thinking about this graph, what would you say the blood pressure is? At what time of year are they gonna be full of blood?
Does it want public schools to understand you?
So what we call ventricular.
That's probably wrong.
Yeah, I did.
I wanna go over there and see how they're doing.
I send you everything.
Wow, that's good pressure.
Okay, that's ventricle.
Did I hear, I hate this? We cannot use negative words in here. No hating.
She's
I'm sure
positive.
she
So
hates
hate is
parking.
a positive word, right? It is supposed to be challenging, okay?
Greater than we.
All right, so let's look at this.
Okay,
So number two,
She hates. She uses it.
It's really just the two
Just the
sides.
entire cardiovascular system.
okay, so during most of ventricular diastole, so for diastole, when it relaxes, the pressure in the left ventricle is what? The pressure in the left atrium. Okay, so when it is relaxed, the pressure is gonna be, think about the pressure in the atrium.
I don't know.
It's gonna build up, right? So during most of diastole, the pressure is going to be less than the pressure in the atrium, right? Makes sense? It is harder. Okay. So let's look at it. So during most of ventricular diastole, so when the ventricle is relaxed,
I really want to get this in the system of our.
is relaxed, its pressure, so here it's going down, so this is flowing. Should be a little bit less. Sorry, it's in black and white, that's why I have this up here. Follow this top line is the
like,
Your ventricles are as full as they can be in your arms.
you're trying to solve a puzzle here, and you're just over there like,
Nobody ever likes this. And I'm not gonna get into cards and different ones on this exam, I just want you to understand how precious things are. That's why this
wrong,
is.
something's wrong.
People never like it. I never had anybody get excited and say, wow, I love this. People just don't like it.
I've been doing a lot of radiation graphs for X-rays,
Yes.
and I'm tired of looking at
Tired of looking at
anything
graphs.
that's like this.
People tend to shy away from graphs. And if I don't do things like this, people ignore that slide. And most times it's like, well, I just kind of skip through that because I didn't really get it. Well, we can't do the matching. I think it can be pretty easy when you know the terms, but maybe a little.
I have some of them, I just don't forget where they go. So I'll want to get you.
Let's go back.
That one, like,
She's like,
What's happening in the atrium?
what are you You gotta go to like New York, California. Well, I would think like, but like in New York, like you have so many people, isn't there like a higher chance? It's a bigger city. Yeah, but I mean, like the volume of people in the city is greater than your city, therefore like you have a greater chance.
no, veins don't have blood pressure. We don't stick arteries. I help them stick arteries. I don't do it myself. Like, they'll stick it in a pool.
Don't know how to drive. It's a scary bro. You don't want to drive. You literally push on the gas pedal as hard as you can to go cruise control, and you let go.
Okay. So let's go over some of the answers. First thing, if you got some of the answers wrong, don't panic and get super frustrated because you will have gotten some of the answers wrong. I've never had somebody at this point say, oh my gosh, I just love the pressure graph, this is so exciting. First thing, people don't tend to like big graphs because, you know, people don't really like graphs. So if I don't really do something related to it, people tend to say, they take the test, well I just kind of flip through that slide because I didn't really get graphs, okay? So this is a little bit challenging because it's thinking about where the pressures go. So first of all, you could follow this exactly from the graph. So what event occurs when the pressure in the left ventricle rises above the pressure in the left atrium? Yeah, the left atrioventricular valve closes. You can see that right there on that graph. Okay? Good there? All right. Now several people will miss this one. So, part B. During ventricular systole, so kind of dissecting this question, what is systole? Contraction. When the ventricle is contracting, what is happening to our blood volume in the atria? Is it increasing or decreasing?
Decreasing.
How many people say decreasing? How many people say increasing? Okay, some of you say increasing because I went by and told you that, right? So let's think about what's happening. When your ventricle is contracting, what's happening to its blood volume? Where's it pushing it? Out into the big vessels, the pulmonary trunk and aorta. So what's happening to the volume in your ventricle? It's decreasing because it's pumping it out. Now, our atria are in diastole when our ventricles are in systole. They're relaxing, but remember they're getting filled because the superior and inferior vena cava are filling up the right atrium and the pulmonary veins are filling the left atrium. So the blood volume in the atria is increasing, right? Now again, that's okay if you missed that, but does it make sense? Can you picture that in your head? Why the blood volume in the atria increases and in the ventricle it decreases? relaxes during ventricular systole. Sometimes it helps to kind of draw that out a little bit. So our ventricle is contracting, it's pushing blood out, so its volume is decreasing. Our atria is relaxing, so it's getting filled. You get there? All right. During most of ventricular diastole, the pressure in the left ventricle is less than the pressure in the left atrium. Okay, great. What event occurs when the pressure in the left ventricle becomes greater than the pressure within the aorta? The aortic valve opens. So that was one you could kind of see a little bit easier there on the graph. Are we okay with that? Please feel free to speak up if something is not okay. I know this is not the easiest thing in the world. Okay, I will tell you part E is the most hard and confusing question on here. The first time I did this and I looked at it, I had to look over it, look at it, think about it, think about it, think about it, because I was like, what? Okay, and then it made sense finally. So, during isovolumetric contraction, pressure is highest where? Let's think about that. Okay, how many people said the ventricle? Who said something else? Who asked that? What did you guys say? Aorta. Aorta. Okay. Why did you say the aorta? Yay! I actually think you're the first group that's got that right, and since I've ever done this, just without help. So, okay, this is hard to understand. But remember, isovolumetric contraction is one of our phases of ventricular systole. It happens right before ventricular ejection. Isovolumetric means that the chamber is full, but it's whenever both valves are closed for a very brief period of time. It's isometrically contracting, so it's building pressure without shortening. It's doing that because the pressure has to rise above the pressure in the aorta. When its pressure rises above the pressure in the aorta, blood will flow from high to low pressure, okay? And it will push blood into the aorta. So, during isovolumetric contraction, pressure is higher than the aorta, but it's doing that so it rises above the pressure in the aorta, so it will flow out, okay? Is anybody like, what in the world did you just say? So, and I wish I had a heart that I could squeeze. I looked for one and I can't find one. Isovolumetric, let me go back here. Isovolumetric contraction. Before these two valves open, we are in isovolumetric contraction. These atrioventricular valves are closed and the semilunar valves are closed. These are completely full chambers with 130 milliliters in them, but none of the valves are open in isovolumetric contraction. They are building pressure, okay? Now, as long as blood is still in here, this pressure has to be lower, and since we're just looking at the left ventricle, we'll look at that one. This pressure has to be lower than this vessel. The purpose of isovolumetric contraction is to build enough tension in the ventricle that this pressure rises above the pressure in the aorta. This pressure rising above the pressure in the aorta is what causes this valve to open. So during isovolumetric contraction, the pressure here is going to be less than the pressure in the aorta. But then it's going to rise above in here at the end of isovolumetric contraction, which opens this valve and pushes it into the aorta. Does that make a little more sense? I realize that's not the most intuitive thing. And then during what part of the cardiac cycle is blood pressure the highest in the large systemic arteries? Ventricular systole, because what is it doing here? It's pushing blood out into the large arteries. That's where their blood pressure is going to be higher. Now, I wasn't going to make you do the matching yet. We have not talked about all of that. What I would do is, at some point, see if you can finish it. It's not super hard. Some of you might have finished it, but we will get to those things throughout lecture and lab. So that's just matching some terms. Did anybody finish that? No? You tried? Okay. We won't go through it just yet. I'll come back to it. Remind me to give you the correct answers, but it will be easy once we've gone through all of that. Okay, what questions do we have over the pressure graph? Now, occasionally I will ask you some things related to pressure. I generally don't give you this whole big graph and ask you to map all of those things out. I just want you to understand those three phases and that blood flows from the high to the low pressure. That's the big point of that, okay? All right, so go ahead and go back to your seats.
I have a question about the from the beginning.
Sure.
What were anastomoses again?
Those are when more than one vessel supplies the same area. It's kind of like an alternate pathway. We'll talk about it in lab too.
Yeah, because they had capillary. Yeah, so like, yeah. Like you have multiple vessels supplying capillaries. You don't want them to get clogged, but like if one gets clogged, you get 12 like
All right. This is just showing a little graph with your end diastolic and end systolic volume. Here's the volume in one ventricle. 130 is their what? What do we call it, 130? End diastolic volume, the pressure in the ventricle at the end of diastole. What's our average end systolic volume? 60, right? 60, the volume in the ventricle after ventricular systole. And you subtract those and you get 70, or stroke volume, right? So this is just showing that. This is the volume in a ventricle. And it's relating that to these three phases of the cardiac cycle. And then we have this nice slide. I know it looks daunting, but now that we've talked about all this, you have done all these parts of it except for the heart sounds, which we'll talk about. I could go ahead and mention the sounds, but we talk about it in lab. But this relates all of those things we talked about. So these phases of the cardiac cycle, the end diastolic volume, end systolic volume, and stroke volume, the pressures, and their EKG. Now these sounds are representing when valves close. What makes your heart make a sound? So what does your heart sound like? Bump up, bump up. They call it loved up. So it goes loved up, loved up, loved up. Really complex words, right? Love and up. The love is considered sound 1. The dub is considered sound 2. Now, I'm not going to go into detail about this right now, and I'm not going to ask you this on the lecture exam. I talk about it in lab. S3 and S4 are called soft sounds that you shouldn't be able to auscultate, which means you shouldn't be able to hear. Now, if there are abnormalities in the heart, you will hear them, and we call those a gallop rhythm. So instead of sounding like loved up, your heart would sound like it said Tennessee, Tennessee, Tennessee. But we'll talk about what causes those in lab. So the heart sounds are made by the, first of all, S1, the closing of the AV valves, and S2 is the closing of the SL valves. Okay. All right. And it will just map it through this whole thing, so this is an active slide. So this is a good way to kind of review everything we talked about today. Just kind of click. All right, so building on what we had over here, our stroke volume is equal to the end diastolic volume minus the end systolic volume. So, cardiac output is the volume of blood ejected from the left ventricle or from the right ventricle, from either ventricle, into the aorta. So if you're the left ventricle, you're going to inject blood into the aorta, or the pulmonary trunk. If you're the right ventricle, you're going to inject blood into the pulmonary trunk each minute. Okay? To find your cardiac output, which we abbreviate CO, you multiply the stroke volume times the heart rate. What's an average stroke volume? 70 milliliters, right? What's an average heart rate?
75 beats per minute.
75 beats per minute. So what might be an average cardiac output? I don't know, we need a calculator, right? Can you put that in your calculator? Thank you, I can't remember. Now people do that, they think they got it wrong, because they're like, that's too big of a number. Remember, this is milliliters, okay? So that's like 5.25 liters. I'm assuming that's right. I didn't do that in the calculator. but it's just 70 to 75. So stroke volume times heart rate is cardiac output. The volume ejected per minute. Now, having said that, I might ask you like one question over cardiac output on the exam for stroke volume. So you can bring a calculator if you wish. Now, I think everybody should be able to do this. But I found out a couple years ago, lots of people are not able to do that. So if you're not able to multiply that way, I would go back and review it. I actually told people in lab a couple years ago that they wouldn't need a calculator on the quiz. And so I gave out the quiz and the hands kept going up. They're like, you said you didn't need a calculator. And I said, you don't need a calculator. So then when I took the quiz up, and this was a really high achieving class, I had probably over 50% of the class that wrote that down, 75 times 70, and just put, sorry, I don't have a calculator and don't know how to do this. And I was like, ah! So it just occurred to me that most people do not remember how to do this that you have a calculator. So if you don't know how to do that, and you don't even know how to teach yourself how to do that, I'm not going to do it right now, but come and see me and I will show you how to multiply. Because I think you should not forget how to do it, but I just realized over half the class could not do that. So anybody looking at that and feel like, I need to do my math again.
Yeah.
Or long division, people don't remember how to do long division. Calculators are bad for us, right? We just don't remember any of that anymore. Okay. Cardiac reserve, this is interesting. That's the difference between the person's maximum cardiac output, so this is higher than this is at rest, and at rest. So this is our cardiac output at rest. Maximum cardiac output is basically what you might be able to do during exercise. So cardiac reserve is important. It's about 4 to 5 times the resting value in an average person. If you are an average person, your heart could probably pump 4 to 5 times this amount in a minute if you were exercising and it needed to, okay? Or, emergency situation, a sympathetic response. So in a very well-trained athlete, their heart has been conditioned such that they usually have a cardiac reserve of 7 to 8 times their resting. That's pretty good because their heart muscle has gotten stronger and they are able to get blood to their organs more efficiently. Okay? People that have heart disease, their heart is not working properly, will sometimes have almost zero cardiac reserve. That's why exercise, if somebody has heart disease and they decide, I'm going to go get in shape, which is good, and they decide, I'm just going to go and run until I pass out, it may not be very long. That may not take very long because they have almost little to no cardiac reserve if they have heart disease. So therefore, their heart is not able to efficiently get blood to the organs and to the brain, so they may pass out pretty soon. So you can train your heart to get a little bit more in shape where it has a higher cardiac reserve. So I'm going to talk about why this is next week. We don't have time to get into it today. But one thing to keep in mind related to exercise is physiological cardiomegaly. And that is healthy enlargement of the heart due to say aerobic conditioning. Exercise. Don't know what that is. So physiological cardiomegaly is good. Healthy enlargement of the heart due to aerobic conditioning. It's like any other muscle in the body. Conditioning that and working it can make it enlarged. And sometimes athletes that are well trained, that do a lot of aerobic activity, will have a low resting heart rate, and that is good because it has time to fill. We'll get into that a little bit next week. Cardiomegaly that is pathogenic or pathological, we'll say, can be bad because the heart can also enlarge due to heart disease and other problems. But due to exercise, that is good. Okay? All right, so one thing I want you guys to just review if you have forgotten it before next week, since we'll talk about it. We're going to talk a little bit about the nervous system and how it influences the heart, but people always forget this. So, some terms we learned at the end of AP 1. Cholinergic fibers and receptors. Versus adrenergic fibers and receptors. You guys remember those terms? No. Does anybody? Okay, raise your hand if you remember the terms. If you remember the words, just if you remember the words.
It's
Okay?
like the nicotinic receptors.
Yes, they relate to nicotinic and muscarinic receptors. Anybody remember what cholinergic fibers secrete? Sorry? Yes, acetylcholine. I'm excited. So what do cholinergic receptors bind? If cholinergic fibers secrete acetylcholine, receptors bind acetylcholine. What about adrenergic fibers and receptors? Okay. You said adrenaline. We also call what? Epinephrine. Norepinephrine. Okay. So we talk about these if people forget those names. I'm glad some of you guys remember. So acetylcholine, norepinephrine. All right. So we will pick this up and finish the heart next Tuesday. If you start studying for anything and you need help, please let me know. Some of this will hopefully help you a little with the case study. Some of the other things we'll talk about on Tuesday will help you a little more. So I'll push the case study back to the 19th. I hope this recorded well.